Hi, I'm Karakus, and I will be talking about our work on Straggler mitigation for NIPS 2017. Many learning algorithms can be implemented through distributed optimization. Under the data parallelism paradigm, the idea is to distribute the data samples across a set of worker nodes and have them receive the current iterate for their parameters, evaluate the gradient on their data partition, and send this back to the parameter server. Unlike centralized computing, distributed computing systems are vulnerable to issues such as network delays and straggler nodes. This slows down the overall computation since the system needs to wait for the slowest nodes in every iteration. This work addresses this issue through the use of data encoding. Given a data matrix X, the idea is to linearly mix the data samples to generate encoded samples, which results in an over-complete representation with redundancy embedded. Note that here the encoding matrix S is tall, which causes the redundant representation. Once the encoding is done, the encoded data samples are distributed across the nodes instead of the raw data, and the nodes operate obliviously to the encoding, meaning they compute as they would with the raw data. In this work, we focus on quadratic objectives, though the idea can be generalized. The encoding is done by multiplying the data variables x and y with a tall matrix S and solving the resulting effective optimization problem. To mitigate the effect of stragglers, in each iteration we only wait for the first k nodes to send updates and move on with the next iteration, where k is a design parameter. The remaining, slower nodes can be interrupted or their updates can be discarded upon arrival. In order for this procedure to find a good solution, we require certain submatrices of the encoding matrix to satisfy upper and lower bounds on its eigenvalues. It can be shown that sub-Gaussian ensembles satisfy this property. We have also empirically observed that equiangular tight frames might satisfy it too. Under this encoded optimization scheme, we show that gradient descent as well as LBFGS with line search is guaranteed to deterministically converge to an approximate solution, where an arbitrarily varying subset of nodes send updates in each iteration. The approximation quality can be controlled by increasing the redundancy factor in encoding or the number of nodes waited for in each iteration. We have implemented the proposed scheme with distributed LBFGS on an Amazon EC2 cluster over 32 nodes. For a ridge regression problem with random data, we find that the proposed scheme can find an approximate solution about 1.8 times faster than if all nodes are waited for in every iteration. We also observed that compared to the data replication scheme, the convergence is much smoother in the worst case. We have also applied this technique to matrix factorization problem for movie lens dataset, which we solved through alternating minimization. Implementing distributed LBFGS over 24 nodes in the high network delay regime, we find that the technique results in more than 2x speedup in the computation while converging to an approximate solution.